everyone, my name is Huang Xiyan. I'm a student from National Hsinchu Girls Senior High School in Taiwan. Today, I'm really excited to introduce my Scratch project, a p-n junction simulator. Through this simulator, semiconductor learners can easily transfer abstract theory into visible phenomena. It's highly intuitive and perfect for anyone who wants to explore the basics of semiconductors. To run this program, you will need two things: a Raboni IMU device and a computer. First, make sure your Raboni device is connected to your computer and named Rab to match the program. Here's how it works. You can control the orientation of the Raboni device to adjust the voltage, magnitude, and direction. The closer the device is to a vertical position, the higher the voltage value. Tilting it downwards generates a positive or forward voltage, while tilting it upwards generates a negative or reverse voltage. Please note that this program only tracks the x-axis sensor as shown on the screen. To avoid detection errors, please do not rotate it along other axes. Now, let me explain what the visual elements on the screen represent. First, we got blue arrow. This represents the electric current. The faster it moves, the larger the current. The slower it moves, the smaller the current. Next, we got the battery. This represents the external voltage source, which is controlled in real time by your Raboni device. You can adjust the voltage to observe how it affects the current and the size of the depletion region. Finally, we got yellow rectangle. This represents the depletion region. A depletion region is an area where there are no freely moving charge carriers. I will explain the principle behind its formation in the second half of this video. Okay, let's see the program in action. Currently, my Raboni device is almost horizontal, so there's only a very weak voltage applied. This direction represents a forward bias, so you can see the current flowing extremely slowly. As I tilt the device closer to vertical, the forward voltage increases and the current flows much faster. Next, when I rotate my device upwards, the voltage switches to a reverse bias. Under reverse voltage, the current remains significantly smaller and limited to a tiny leakage current. However, if the reverse voltage goes too high, it triggers a junction breakdown, causing the system to experience a sudden surge in current. I'll break down the detailed physics behind this shortly. Now, I will explain how this program works. Class begins. First, what is a semiconductor? Simply put, a semiconductor is a material whose electrical conductivity lies between a conductor, like copper, and an insulator, like rubber. Because of this unique property, its behavior can change drastically based on external conditions like temperature or voltage. Second, what exactly are we observing in this program? As you noticed earlier, the main star of our simulator is the yellow rectangle, the depletion region. You see, a p-type semiconductor is full of positive holes, while an n-type is full of negative electrons. When they join together, electrons and the holes near the brother rush to meet each other. This leaves behind a middle zone with no free-moving carriers at all, leaving it completely depleted. When we use our Raboni device to apply a forward bias, we force these carriers back into the circuit, making the yellow rectangle shrink and allowing currents to flow easily. But when we apply a reverse bias, we pull them away, causing the yellow rectangle to expand and act like a sturdy dam to block the current. But wait, what happens if the reverse voltage gets too high? This brings us to a fascinating phenomenon called junction breakdown. When you tilt the Raboni device too far upwards, the high reverse voltage creates an instantly powerful electric field. This field acts like a strong wind that rips electrons out of their atoms. These electrons crash into other atoms like bowling balls, creating a domino effect called avalanche effect. The voltage at this point is the breakdown voltage. Once we hit it, the dam breaks, and a massive flow of current rushed through, causing the voltage collapse you saw in my simulator. Now, let's do a quick review. First, under forward bias. The higher the voltage, the stronger the current flows. Under reverse bias, the current remains extremely small and constant, no matter how much you increase the voltage until the voltage exceeds the breakdown voltage. Once that happens, it triggered a junction breakdown, causing the current to suddenly spike and flood the system. So that's all we got for today. Thank you so much for listening. I hope you enjoyed the learning process and learned a lot about semiconductors. We'll see you next time. Bye bye!